Hello and welcome back again. We're going to continue our overview of the synthesizable subset of Verilog by now looking at functions and tasks and illustrating them with a more complex example, a linear feedback shift register. Functions and tasks are quite useful in both design and very useful in the test fixture. What they allow you to do is within a module capture common elements that are repeated through the module in one piece of code. You then call the function or task in order to execute or implement that particular function. So that way it saves typing, repetitive typing of common structures within a design. Function and task themselves are a little different in terms of how they're treated in simulation and synthesis. Function takes multiple inputs and returns a single output, whereas task can return multiple outputs. Both of them must be called from within the module that they're built in. So you don't implement function and task outside modules, you implement within a module and only use it within that module. Function cannot contain any timing, such as @ statements or triggers. Task can contain timing, and this can be quite useful in test fixtures, but you cannot use it in logic. It cannot be used for synthesis. So here's a relatively complex example that I'm going to illustrate with function and task. What we're building is a linear feedback shift register. Show the logic first. A linear feedback shift register is a register that feedbacks on itself such that you can produce a pseudo-random sequence of numbers. The specific sequence of numbers depends on the initial number loaded in on the reset, and also depends on the taps, that is, where these XORs are in this feedback chain where you take the lower order bit and XOR it or not with an aggregate of all the bits before to determine the D input for that flip-flop. The actual sequence depends on these taps where the XORs are and is varied by setting those taps appropriately. Here in this illustrative example, taps are set at 0, 1, 0, 1, 0, 1, 0, 1. In the code are going to have different values of taps. Linear feedback shift register is very useful for when you need a pseudo-random number that can be produced from synthesizable logic. For example, a lot of cryptography. For example, where you want to randomly direct vectors within a unit to different things that can bear their load, and so on. It is a pseudo-random sequence because once you determine the seed and the sequence is then fixed. By the way, there are ways of producing purely random numbers in hardware, for example, from thermal energy, but these are not synthesizable and thus they're beyond the scope of the class. So here we have something very similar to the structure I just showed you, with a function being used to implement the combinational logic. Let's go down the bottom here first to the two LFSRs being used here. The only point of using function or task is to build multiple replicas of this logic. So I've illustrated function and task with two LFSRs built using the function or task. You'll see here we have always at pos edge clock or neg edge reset. Reset, you recall, is a golden signal coming from outside your design, used to put the design into a known initial value. Here it's put into seed, which is different for each LFSR. This is the initial pseudo-random number. By putting or neg edge reset here, you might recall we're making reset asynchronous with clock. Whether you choose to make it synchronous or asynchronous, if there was no or neg edge reset, the reset will be synchronized with the next clock event. It's up to you which you choose. Just be consistent throughout your design. Once we're beyond the reset, what happens is we call this function, LFSR taps 8 function, using the input of the current value of the pseudo-random number, y1, and that's assigned to the output, y1. This might seem a little strange, both the input and the output are the same, remember this is separated by the rising edge clock event. That is, the input here, Y1, are the outputs of the flip-flop from the previous clock cycle. And when we call the function, we're generating what the outputs of the flip-flops will be after the rising edge clock. That is going through, we're really generating the combinational logic, what the D inputs are, and when the rising edge clock event is over, those then become the next clock period's value of Y. So, Y1 is sent to this function as an input. For a function, just like in other languages, the name of the function is the output. You see that down here, LFSR taps underscore FN is being assigned. And here we're listing the inputs. There's only one input here, so we're excuse me. So we're listing A as that input and specifying its width, as well as specifying the width of the output. Here we have a local parameter taps, which defines the actual sequence. And here we specify the types and the vector ranges of local variables that are used within the function. Let's see what's being done here. First of all, we are producing the NOR gate that you saw on the next page. That's then fed into an XOR gate. Then we use a for loop to iterate through the vector, or through the array of bits as I've called it previously. If taps n-1 is high, we're implementing an XOR gate. If it's low, we're just taking the previous value coming into the function. The 0th bit is just set equal to feedback. So that's what we have here. Here's the first two gates in the function. Here's the for loop. When taps is high, we're implementing the XOR gate. And again, the pattern here is actually different than the one on the previous page. And this feedback is just sent back to bit 0. Here we have another LFSR. And its only difference is it starts with a different seed. Seed 1 and seed 2 are specified up here as parameters. Otherwise, it's the same. The input to the function is the current value of Y that goes through the combinational logic, producing the output of the function, which is the next value of Y. Of course, one thing to note here is if we chose not to use functions, we'd still have to implement this logic up here as a logic procedural block, because we're naming these signals, bits 0, underscore 6, underscore 0, and feedback, and we want those to be the output of combinational logic, so this would have to have been an always at star block. So that's the use of function to capture repetitive logic, i.e. the logic that's repeated between these two LFSRs. Then that logic is identical in this case. Here I'm going to illustrate a similar but slightly different example using task. And here I'm going to illustrate how we could use task to specify different logic for the LFSR combinational logic. So here I'm going, just for the interest of saving space on the page, I'm only actually going to build one LFSR. Let's go down here to the synchronous logic. On the neg edge reset, Y1 gets initialized to seed1. Seed1's a parameter. Then we call this task. Y1 and taps1 are now inputs. Y1 is also an output. Remember, that's the next value of Y1. Taps is now a parameter at the top level of the module. It is specifying where the XOR gates are in the feedback structure, and thus a pseudo-random sequence. If I wanted to, I could have a second parameter, taps2, up here, write this code out a second time for Y2 and taps 2, and produce a second LFSR with a different sequence of pseudo-random numbers. In contrast, the function implementation I had 2 pages ago, each LFSR produced the same sequence, just at different starting points. Let's now look at the task itself. The inputs and outputs of the tasks are specified here. We have 2 inputs, A and taps. 1 output, next LFSR reg. The order here matters. Again, Y1 and taps 1 are inputs. Y1 is also an output, but remember this is the next value of Y1. An integer n to iterate through to control the array of the for loop that's used to iterate through the array. Bit 060 and feedback as before. We've also declared the output because it has to be declared as type Y or type reg depending how it's assigned here. It's assigned procedurally here, so it's type reg. We then go through the steps in the logic chain that produces the next value of the pseudo-random sequence at Y1. Again, building the NOR gate, building the XOR gate, iterating through the array of bits. When taps is 1, build an XOR gate. When taps is 0, just feed the logic. Bit 0 becomes feedback. The output of this is next LFSR reg, which becomes Y1 here, which is connected to the D input, essentially, the flip-flops, and thus becomes the next value of Y1. Notice that taps has to be a fixed set of numbers. It cannot be a variable. Right? Taps was fixed up here as a parameter. If taps was a variable, we'd be building variable logic. That is, as taps changes, the XOR gates change. Can't do that. Right? If you need to do that, then you need to put in some muxes and control lines, and taps needs to be in a register somewhere. That's a different design. That is not the design that's intended here. Here, we're iterating through a fixed pseudo-random sequence as specified by taps. We can build different combinational logic blocks by changing taps, but taps is not a variable. It's a constant. And again, we're building something similar to what you see on this page here. So that's function and task is used in LFSR. Again, note, no timing within function and task when it's synthesizable. If you're using function and task in a test fixture, you can have timing, and we'll show that later when we talk more about verification. The last, more complex example we want to look at, it's also quite a general, useful structure, is a register file. It's very common to need an array of addressable registers, and this module shows you how to describe one. So here we're actually going to be building 32 16-bit registers. We're building this as a 1D array of those registers. So each register is 16 bits wide, and there's 32 of them. We're going to have one write bus and read bus going to this register file, one write address and read address going to this register file, as well as a clock for writing, and WE means write enable. When write enable is high, we want to be able to write to the register that's specified on the write address bus, write the value that's on the write bus to that register. Here's our logic internally. First of all, what we're going to do is produce address lines, 32 of them, one for each register. The idea is if W lines is high for that register, we'll write to that register. This is quite an elegant way of specifying how this will behave. W lines is 32 bits wide. If write enable is high, it's going to be shifted left by the amount write address so as to enable that particular WE lines. Let's actually look at this on the next page. Here's that logic I was just describing. If WE is high, it's shifted onto the correct WE lines by write address. So for example, if write address is 0, it's shifted 0 bits to WE line 0. If write address is 31, WE is shifted left 31 bits onto WE lines 1. If WE is 0, all of these will be 0. If WE is 1, only one of these will be 1. And that's what we want. We only want to write in this one ported register file to one of the registers at any clock cycle. Here is the actual write. Again, because we have an array, we're going to use a for loop to decide which to write to. We go through the for loop. If W lines is high for that particular register, then we're going to write to that register from the write bus on the POS clock event. This is a register file of flip-flops. Read is done basically through a multiplexer. Before, I've illustrated using an index into an array to build a multiplexer, and that's exactly what we're going to do here. Read address is that index. Register is the register array file. So again, this is the structure we're building. If WE is 1, it's shifted onto the appropriate write enable lines. That causes that particular register to be written from the write bus on the rising edge clock. The read bus is simply connected to the output of this mux, who's indexed by read address. This is a very general structure. It can be used to add ports. We're actually also going to use this to model the SRAMs that we'll be using in our designs later. I want you to note some things here. This is really an array of vectors, not a true 2D array. And unfortunately, arrays of vectors cannot be passed in port lists. Here there's no need to pass them. Later we'll see an example in the complex design notes where it actually would be desirable to pass them in a port list, but we had to avoid that in the actual code. And by the way, we could have encoded the write structure by not having an explicit write address decoder, but we could have done it with an implicit write address decoder, something like this. Again, it'd be a sort of a demux structure. If write enable is high, register indexed by write address is written from the write bus. So this would have actually been a demux up here going to these arrays with write address as an enable to these registers. This is less typing than the example I had in the previous page, but because the address decoder is not explicitly broken out, it goes into this mux structure. This actually turns out to be slower and to take more area. Again, it's a brief illustration of how adding human-derived knowledge, that is, we want to build this with an address decoder, we're decoding write address onto one of these lines, leads to a more efficient design. And we've seen examples of that before in comparators and adders, where adding human-derived knowledge has made a more efficient design. So that brings us to the end of this particular submodule. We've illustrated how task and function can be used to capture replicated logic. And I've given you the general structure of a register file which uses an array of registers. I now ask you to take the submodule quiz for this particular submodule before proceeding to the next and last submodule for this unit and module. Thank you very much.